Why is the trend now moving towards GPU, especially for fluid mechanics simulation?
GPU is actually a bit slower than CPU. In our case, the amount of code is 7 million lines. They just write the code, the framework takes care of the rest. NVIDIA was, in terms of framework and compiler support, way ahead of the curve. Without CUDA, it would be very difficult to code like ours. Advantage of this approach is that we have the same code for NVIDIA and for AMD. Even these cheap Maxwell cards can give you enough performance to justify the larger scale development. Volta was really the first HPC generation GPU. When it comes to these benchmarks, you can create pretty much any numbers you want. Lots of the national labs code now will not run unless they are also GPU enabled. C++ is probably today the best language to learn. Not everything can be nicely expressed as finite volume. When you get that last loop out, suddenly the code becomes 40 times faster. This scheduler that runs somewhere inside the GPU hardware, you have no control over that.
This podcast is sponsored by Siemens Digital Industry Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with Simcenter. Alright, ladies and gentlemen, today I have a very special guest on the show, namely Petr Kodl from Siemens, and today we'll talk about GPU, accelerated fluid dynamics, and high performance computing. But before we jump into the nitty-gritty, Petr, can you give the audience a little bit of a background, like who are you and what are you working on at Siemens?
So, hi, my name is Petr Kodl. I'm a director of the architecture group at Siemens, but my original background is mostly the software framework behind STAR-CCM Plus and general HPC. So I went through several different tasks since I joined. I started with really just general HPC due to non-compete agreements, then discrete element methods. After that, some finite element codes, and as kind of side project, I started this whole GPU initiative. And at the moment, I'm basically responsible for some of the core architecture of the product. So that's my background. And in terms of schools, I started with nuclear physics. It looked like a great idea until Chernobyl.
Yeah.
And then I switched more towards like general math, and the actual program was called mathematical engineering. So it was always oriented towards like practical applications, not pure math, not so many proofs, but more numerical methods, stuff like that.
What fascinates you about the topic, Petr? Because I always like to get out the intrinsic or extrinsic motivations behind why someone likes their subject so much. Like, what was the motivation for you initially?
I always like video games, and then somehow this whole simulation felt like it's like video games, but more accurate. So, and I was always attracted to computers. My whole family is basically either nuclear engineers or turbo machinery engineers or mathematicians. So I really didn't have a choice when I think about it. It was my destiny probably since day one.
I guess, yeah, even before we talk, before the podcast, you had a lot of great anecdotes, which we'll talk about today's episode. A very simple question, and ignore my ignorance, by the way. I said that before the podcast as well, because I just had one course in uni, and you're the expert here. But let's maybe start very simple. What is the difference between a GPU and the CPU, and why is the trend now moving towards GPU, especially for fluid mechanics simulation? Maybe you can talk a little bit about that.
Yeah, so it's an interesting question, right? So when the GPU started, nobody really knew what to do with those things. It was like niche market for video gamers. But I think around, I would say 2000s, there were these first papers that started popping up where people were really kidnapping these very graphically oriented frameworks, and they try to make them do things that look a lot more like simulations than like a video game. So there were these original papers talking about how do you make particles compute on the GPU and how can you do it using vertex shaders. So it was very primitive in terms of software engineering. It was like everything was a bit hacky and hand coded, but so not really suitable for like large simulation framework. But then CUDA showed up, and CUDA really changed the game. So suddenly you could write these GPU codes in a way that you would write normal C or C++ software. And in terms of architecture of the chip, the main difference is, in principle, GPU is not fast. GPU is actually a bit slower than CPU,
Hmm.
but it has a lot more cores. And the limitation is that in order to get good performance, these cores kind of all have to do the same thing. But it turns out that for simulation of our kind, meaning finite volume, finite element, particle methods, this actually fits. It really fits the bill because all these chips are kind of in sync, computing something very similar. So, and to be honest, we already had that model. It's a similar model that you have in the typical NPI computation, where you want to try to run the same code on all the cores, on all the CPU cores, just computing with different data. We are just making it much more fine grained. So that really worked for us in a way. And there are some other advantages of the GPU because they don't have this legacy going back to like Intel 8008. They don't have to honor the memory model. They don't have to honor any volatile pointer, right, will trigger some sort of memory synchronization barrier. So there is a lot less silicon dedicated to these things that we actually don't need. And that's a fortunate thing for the GPU and a bit unfortunate thing for the traditional CPUs. They cannot depart from this memory model. They cannot now decide that some of these things that we were kind of not directly but implicitly promising, we will violate it because everything will stop working, right? So the way the code is written, it assumes certain things about CPUs, and GPUs don't have this heritage and legacy. They are free to do something a little bit better. So, for example, you don't have to synchronize all the threads all the time until you really want to. You can make certain things more explicit, and that gives you more
Hmm.
performance. So there is a lot less silicon on the GPU chip that's dedicated to these kind of implicit synchronizations and syncing the cores across the bus and all that stuff. So,
I see. Yeah. How does it look from the memory hierarchy point of view, and what are the implications, especially when you code a fluid dynamics code?
so the memory hierarchy is a lot more shallow. So typical CPU chip has like L1, L2, whatever, L3, this very deep cache hierarchy and very complex rules about how these caches are being synchronized. GPU tends to be, there is one level cache and there is a shared memory and there is a lot more control, explicit control over that memory hierarchy than you have on the CPU side. On the CPU side, it's basically nobody does this manually anymore. Everything is done either by the chip itself or to some degree by the compiler. But on the GPU, this shared memory is quite often still manually controlled when you want to squeeze out the remaining 10% or last couple percent in the algorithm. So, and for the finite volume code, we are actually not in bad shape because the main memory of the GPU is way faster than main memory of the CPU. So, and GPU is really throughput oriented. So when the threads have nothing to do, the internal scheduler switches them around and it finds some that can actually do work. So this throughput oriented architecture for methods that discretize on some sort of mesh or particles is actually very well suited for that type of computation.
I said
So
that's interesting. When we think about the practical coding aspect of it, and Peter, you're the expert there. I was wondering what are some of the intricacies or maybe the difficulties when you want to implement fluid dynamics code on a GPU?
So I wouldn't say fluid dynamics would be that complicated. What's
Hmm.
complicated is doing it for a code that's as big as ours. So you can find very simple flow codes written in a couple hundred lines, but
Yeah.
they will be missing the richness of the modeling that, in our case, STAR-CCM Plus has.
Hmm.
And the task that was ahead of us when we decided to go for this GPU coding was basically comparable to swapping out a car transmission while we are driving.
Yes.
Because we can't simply stop development, throw everything away, and start from scratch. We have
Yeah.
existing customers, we have lots of knowledge that's implicitly embedded in the code that is not like the gradual textbook type of algorithm. It's lots of know-how about making the code more robust for bad meshes, and you always
Hmm.
get bad meshes, right?
Hmm.
So meshes are never good,
Hmm.
and so you have to basically be very careful how you approach it, such that your original code doesn't suffer. And in our case, the amount of code is, yeah, 7 million lines, give or take.
Hmm.
So now we had to approach it in some constructive way so we wouldn't lose the existing customers while they are waiting for this amazing GPU code to show up. Right? So
I see. I see. When it comes to high performance compute, or maybe the journey going back to your early career, how do you see the transition going from CPU to GPU? Like what sparked the initial idea, apart from CUDA that you explained a couple of minutes ago, to go the GPU route? And do you think it will change in the future? Like, will there be something else coming?
probably, I don't have a crystal ball, but
Yeah.
I would say yes, because there are already, even the GPUs are now perceived as consuming too much energy, and
Okay.
specifically in this AI domain where the throughput is super important. There are already chips that are way more specialized than GPUs and they can run the same code cheaper. The question is always, can you take chip like this and design a framework that will allow people who know the physics very well to write code such that the CPU code and the chip code looks very similar. So, and that's the challenge for what we are trying to do. And we managed to do that before with the MPI. The guys who write the physics and who know all the idiosyncrasies of turbulence models and evaporation models, they don't have to think about the fact that they are running in the MPI environment. They just write their
Hmm.
code and the framework takes care of the rest. And our goal since day one was to do something similar, but do it now in this CPU GPU domain. So at the end, uh, we couldn't change the code. What we had to do, we had to change the framework. Once your framework is ready, the rest of the code looks the same. And we, to a large degree, managed to do that. There are some quirks because those two architectures are not exactly the same. So you have to be a little bit aware of the fact that technically speaking, the GPU is another machine running inside your machine. So you don't have a single memory pool as on the CPU. You actually have memory that belongs to the GPU and a memory that belongs to the CPU.
Hmm.
And of course, what's happening now is these, what I would call super chips that are coming out of NVIDIA and AMD, like the Grace Hopper and MI300. They are trying to unify even that aspect. So instead of having a GPU card that has 80 gigabytes of HBM3 memory, they are trying to make it look through the kernel paging such that the memory is really unified. But somewhere in your head, you still have to be aware of the fact that there are two different memory banks, basically.
Yeah.
And as much as you can hide it, from time to time there is a copy, and that copy will hurt you if you don't manage it well.
I see. Um, Companies like NVIDIA, are they providing developers like yourself with kind of frameworks to help you write better code or more efficient code? How does that
They
work?
are providing lots of material. They are NVIDIA was in terms of framework and compiler support way ahead of the curve. So to be honest, without CUDA, it would be very difficult to port code like ours. Um, what really made it possible, I think, is a couple of years ago. Well, it's more than a couple today, but around the CUDA generation 8, they introduced this concept of an extended lambda, which is basically an ability to capture anonymous function in a way that you can have the same function running on the CPU or on the GPU,
Mm-hmm.
and the switch point can be embedded in your code. So this really allows you to now design code in a way that you don't have to have explicit if statements, and you don't have to that actually differentiate between GPU and CPU path. And you can have really uniform code running on both sides of the memory bus. So, so these extended lambdas, they were kind of the last larger missing piece. And of course, longer term, specifically with languages like C++, the goal would be to embed enough of this parallel abstraction such that instead of writing anything specialized, we can just write standard compliant C++. And if you look at the C++ standard committee, there is lots of NVIDIA people embedded in that group, and they are trying to steer a little bit this whole modern standard high performance C++ towards that goal. But we are not quite there yet. So if you design your code from scratch today and you are careful and you are using a well-chosen subset of C++, you might be able to write your algorithm in complete uniform way.
Mm-hmm.
But it's not 100% that simple. So you
I
still have
see.
to be aware of these idiosyncrasies.
Yeah. Maybe a super weird question, but when you write code, Peter, is it that you write CUDA specific code, so for NVIDIA graphic cards, or does the code differ how you write it for other graphic cards?
Uh, no, so we got inspired, to be honest, by some of the high-level frameworks that started popping up specifically after these extended lambdas became available. So there are a couple from these big US national labs. There is a Cocos, there is Raja. So they are basically frameworks where it's a wrapper around CUDA. It still uses CUDA behind the scene, but the wrapper
Okay.
provides high level of abstraction, and lots of the heavy lifting is done upfront in the compiler through the templating and specializations, and so basically the standard C++ tricks. And we actually originally wanted to use one of these frameworks, but then we looked at our framework that we already had in STAR-CCM Plus, and sort of by either sheer luck or like really genius ideas of the original authors of the code, we were pretty far through already. So we didn't have to throw everything away and adopt a new framework. What we had to do, we had to tweak our existing one. And once we did that, we pretty much got something that on the surface it looks exactly the same as before, but inside it works more like these modern C++ frameworks that are GPU enabled. But advantage of this approach is that we have the same code for NVIDIA and for AMD, for example. We don't have to,
Okay.
and for the CPU and for multiple kinds of CPUs. So our
Hmm.
ARM code, x86, 64, CUDA, AMD, it's the same code. You cannot, there's no difference in
I
the
see. Okay.
syntax or semantics.
I see. Okay. Going back to the development side where you talked about kind of CPU optimized code versus like you went the GPU route, how did you actually develop that? I think from a developer point of view, that would be interesting for the audience. Like, did you start a parallel stream with a sub team and then develop the GPU code in parallel, or how did that happen?
So the CPU code existed since around, I would say, 2000. So that's
Hmm.
relatively mature code. By the time we got to it with these GPU ideas, uh, it was more how can we change the framework such that the GPU will start working? And the way we did it, we started with a small prototype. So basically took some of the core concepts. For example, how do you write a loop over some stencil, which in finite volume is the daily bread and butter, right? I'm looping over the cells, I'm looping over the faces, reaching to the cells. Can I take something like this and abstract it out such that it will look the same for the CPU and GPU? Then what you need also is a little bit of an abstraction over the memory management. So how do you make sure that when you start looping and you are accessing these individual cells or faces or vertices, whatever is needed for your particle equation, that the memory is ready at the correct site. So either it needs to be the GPU memory or the CPU memory, depending on which context you are operating in, right? So these were the things that we had to figure out first. There were a couple more. How do you, for example, represent things that are not just simple memory accesses, but they also represent some embedded computation? So and I think it's kind of inevitable in any larger scale code. You are trying to always abstract some complicated variables that are more like expressions. They are basically small computations that are done locally on element by element or cell by cell basis. So things like material properties, or I have pluggable definition of how my viscosity is defined. So what happens typically is these are variables that have some other dependencies, and that whole tree of dependencies, including the AST that represents the expression, has to somehow travel to the GPU and be computable there. So that was another thing that we had to figure out. And the last thing is, of course, when you compute on the GPU, on the CPU, even in the NPI context, they are computing sequentially. I have a stencil that has 2 million cells. I'm going through these cells from beginning to the end. So it's a kind of nice for loop, right? There's a counter goes from 0 to n. So the typical computer science 101. On the
Yeah.
GPU, it's not like that. You basically take that whole loop, you turn it 90 degrees, and you shred it through at the same time. So all these indices are firing at the same time. And that kind of gives you this amazing performance. But on the other hand, it also takes away some tricks that you can do on the CPU. Like, what if I cache the value from the previous stencil for my next cell? You cannot do that simply because there is no next, there is no previous. It's all done based on this scheduler that runs somewhere inside the GPU hardware, and you have no control over that. So, and this prototype actually gave us some initial idea how fast the code could perform. And we were doing all of this on like very low performance Maxwell graphic cards. They were the standard Quadro 4000, whatever you can get in your workstation. But it started to look pretty promising already. And and then we decided that this might actually work because the framework itself looked like it could be done. And then we basically ended up implementing in a couple weeks like an end-to-end piece of code, which was just a simple Laplace equation, but really all the way from boundary conditions, discretization, and a linear solve. And that really gives you a rough idea of what the potential performance gain could be. And it looked pretty good. So we basically realized that even these cheap uh, Maxwell cards can give you enough performance to justify the larger scale development, because the Maxwell at that point was, it's like 2013, 2014 generation of GPUs. And by the time we were working on the code, Volta was coming up. So it was like 2017. That was the, Volta was really the first, what I would call HPC generation GPU, because it had very good double precision performance. It could do double precision atomics that were pretty much burned into silicon. So the STD atomics for Volta were like really well done. And it also implemented properly the C++ forward progress model. So meaning that if you have a log somewhere in your computation, the whole thing won't just stop. It will actually progress forward. So
Hmm.
this is something there's inside C++, there's this embedded virtual machine which actually specifies what should happen when there are multiple threads and some of them have been logged, but some other ones can progress. There is actually no guarantee in principle unless you make some specific assumptions that the code that behaves like this will move forward. But with Volta, this was actually for the first time where NVIDIA made this formal promise. Previously, it kind of worked, but it didn't have to.
I see.
So
We were definitely now talked about the speed aspect, which I think from a business point of view is like incredibly attractive, right? But what about accuracy? How do you ensure accuracy when coding on a GPU or CPU? It doesn't matter. Like, how do you do it as a programmer?
So as a programmer, there are certain things you have to learn, right? There's this famous paper what every computer science or simulation developer should know about IEEE floating point format. But in principle, the way we write the code, we are always trying to drive some residuals to zero. So there are a couple things that, unless you code in a really bad way, like dividing by large numbers by small numbers all the time, the finite volume code is relatively friendly towards the IEEE format. And we can, for most cases, get away with 32-bit precision. We don't actually have to go to full doubles, which is actually really nice for the GPUs because most of the cards that you get over the counter, so I don't mean these super high performance data center cards, perform well better, way better than in single precision than they perform in double precision. In terms of there is a multiplication factor that can be 1 to 2 for the HPC class cards for the really expensive ones, and up to 1 to 32 for the cards that you typically get for gaming. Right. So if you need to compute everything in double precision and you are not memory bound, the card performs way poorer in double than it performs in single. So,
What if we talk about energy efficiency? CPU. I think you touched on it a couple of minutes ago. CPU versus GPU, and is there a cap on how far we can get as coders, or maybe regarding the performance of a GPU, and when it comes to energy efficiency?
so energy-wise, they are really good because they are missing this large chunk of black silicon that's doing nothing useful other than synchronizing the cores versus each other. So in principle, the small cards are somewhere around 130 watts. The larger cards from NVIDIA are now in the neighborhood of like, I believe the A100 is somewhere around 300 watts. But for the 300 watts, you are getting performance of several CPU racks, right? So in terms of energy consumption, it's actually very good.
Hmm.
In terms of performance, if you can keep the cards busy, then they perform well. And busy, I mean, for a typical finite volume code during the discretization, if you want to keep the card occupied at 99%, you need roughly 2 million cells to provide enough work. Otherwise, the card is basically sitting there doing nothing, right? So for the super small problems, and that's kind of along the way of GPU as GPUs are very good for throughput. So if your problem is too small, you are not winning much because the
Hmm.
throughput you don't have enough work to do.
Yeah, is there like Peter? Sorry for interrupting. Is there like kind of a switch statement where it says if the problem is too small, like there's not enough cells, you just use the CPU? Is
We
that how
don't
it
do
works? Or?
that. We
Okay.
leave it to the user. So we have a basically the way our code is designed from the workflow point of view. We have a command line switch that says I want to run on the GPU.
Yeah.
If it finds one, it will use it. But we don't try to be smart about the size of the problem. We
Okay.
provide some documentation to the user, and
Hmm.
it's kind of same thing for all the HPC codes. We let people make these decisions even when it comes to MPI. You can oversubscribe the nodes, you can undersubscribe the nodes. Typically, coming up with, we provide recommendations, but we don't set up hard boundaries anywhere.
I see. Okay. Going back to the energy efficiency, was there anything else we missed? Like, especially, I think before the podcast, we kind of talked about the comparison between efficiency of codes. Like, can this be trusted, or how do you actually measure accuracy, speed, etc., when it comes to GPU performance?
So we try to provide some numbers that give you a hint how many CPU cores are roughly equivalent to a GPU card.
Hmm.
And for typical finite volume problems, we are getting somewhere in the neighborhood of 100 cores per card for the volta generation, and we are approaching 200 with the ampere. And now with the latest, greatest, the Hopper, we are pushing like 250. So, but these numbers are guidelines. Depends on size of the problem, depends on the structure of the mesh, how many computational nodes do you need to fit your whole problem. So the individual card computational density is way higher than what you can get from a typical cluster node. That's not disputable.
Hmm.
But if you need to run problem that you need to spread across 80 cards, meaning typically 10 high performance DGX capsules or something along those lines, the overall efficiency will suffer a little bit more than it would typically for the CPU because the MPI exchanges become comparatively more expensive because the MPI needs to basically grab the memory from the GPU depending on the specific implementation. Sometimes they can route it directly through the NVLink, sometimes they need to route it through the main memory and some sort of InfiniBand. But this exchange, because the GPU is so much more powerful, hurts you more. So typically what we see is if the customer can fit a given problem to a single card, they are getting this optimal efficiency.
Hmm.
We can still scale up to, I think we ran probably by accident at some NVIDIA cluster with like 300 cards. And the code will still scale, it will run. But at that level, you will probably not be super efficient because the MPI is proportionally consuming more and more resources. So.
I see. Yeah. What do you think some people get wrong? Like when you read papers on efficiency, code speed, and all the other methods that exist out there, like SPH, for example. What do you think a lot of people get wrong in terms of speed and accuracy of specific codes? Because sometimes I feel, especially plots in terms of accuracy, speed, etc., are demonstrated in such a way to make the authors look good. I'm not sure if you would agree or disagree there. Like, what is your
You can,
experience?
when it comes to these benchmarks, you can create pretty much any numbers you want,
Yeah.
right? And now it depends on a typical customer case. So if we know that, so we are typically developing these days for customers who are running meshes in the neighborhood of 160 million cells. 10 years ago, large mesh was 20 million.
Hmm.
Today, 160 is considered medium sized mesh. People have, doesn't matter how fast you make the code, it's only one day where you can kind of be famous because you made it faster. Tomorrow, the customer will double the mesh.
Yeah.
Right. So we are basically optimizing for these 160 million cells, which is kind of nice for the external aero. We ran cases on GPUs that were approaching 500 million. We don't run typically cases that are that large in house. Uh,
Mhm.
but now what you can do is you can take this case and you can measure the performance of the GPU nodes. And then you can start increasing the number of CPU cores and see what is gonna be this equivalent, right? And depending on how you set up your GPU case, at some point the CPU scalability will stop scaling. It will not get any better. And you can basically proclaim that your GPU code is indefinitely faster because you can never reach asymptotically that same performance on the CPU. You will simply run out of scalability. But that's not fair, right? That's not a fair comparison because you need to consider resources, you need to consider how much do you want to invest, how much total time do you have available. So yeah, it's a tricky thing to do. It really depends on specific customer, specific setup.
Yeah.
We provide these rough guidelines to give people an idea, but ultimately we always say measure. Set up your case, try to use best practices, uh, and measure the time to solution and decide is it worth for you to use the card in a little bit more efficient way and maybe run a little bit longer? Or do you want to get best absolute performance, throw in more GPUs, but don't use them as efficiently as if you have the number of the GPUs, right?
I see.
So
Yeah. You talked about the 500 million cells that you run once. Is there a theoretical limit of how many cells a problem could have?
theoretically, no. We will probably at some point, depending on the internal representation of the mesh, start overrunning some indices. So what happens in typical finite volume code is you have these direct stencils like cells that you iterate through, but you also need to iterate through stencils that are indirect. So when you walk through the faces and you want to accumulate some fluxes, you need to reach to the cell on the left and cell to the right. And for this, you need some sort of indexing schema. And this indexing schema can either be done in terms of 64-bit indices, which gives you essentially unlimited range, but it also costs you memory, right? You need to fetch these indices from memory all the time and then jump through them. So it's expensive. So what we are doing at the moment in our code is we use 32-bit indexing. So yeah, if we run billion cell case, uh, I think if you have nodes with lots of memory, you can basically overrun some of the indices, but we can detect that upfront. So we will tell the customer, yeah, so this case will not run because you need basically more nodes. And once you throw in the extra nodes, that index range will shrink again to a reasonable range. So
I see. Okay, yeah, got it. Maybe in terms of your career, maybe some advice for the audience there. How would you recommend people getting started, maybe coding on a GPU? What is some of the small cases they could get started with, if they want to delve into the field and become someone like Peter?
I don't know if you want to become me, but no. So I think it's very good to follow the trends, right? So NVIDIA is making the standard C++ more and more compliant. So that's definitely one track. GTC is still very good conference, despite the fact that the large language models are now ruling the world. But there is still a slot somewhere, like dark corner, where the HPC guys can talk. Uh, the national labs have very good codes and very good examples. Lots of the national labs code now will not run unless they are also GPU enabled, because all the large machines they are building have the GPUs as the main workhorse. The CPU is just sitting there, basically synchronizing these GPU kernels. So that's really nice. So both Cocos and Raja come with lots of really nice small tutorials, and you can compile them locally and run them even on a relatively inexpensive GPU card. Uh, and then follow the trends, because whatever you learn today, given the speed of development in this domain, which is to large degree driven by the AI, but fortunately for us, it benefits the HPC because we are solving very similar types of problems. Uh, what you learn today in 1 year might be totally different. I would
Yeah,
probably still recommend to understand C++ well because it's a dominating language uh, at the moment. Uh, some of the other ones, there are some niche areas where specialized languages are winning, but in terms of a language that provides decent level of abstraction, decent type system, and at the same time, this very low level direct hardware access, C++ is probably today the best language to learn.
I see. What do you think about Fortran?
Fortran is amazing, but it's harder and harder to find these new large frameworks that are written in Fortran. So
Yeah,
this it's missing a little bit in terms of numerical performance. It's actually a much nicer language than C++ for the compiler to optimize because the language is simpler. It doesn't promise as many high-level constructs, and some of the constructs that are optimizable are actually expressed directly in the language. Some of these array expressions, they are just written directly, so the compiler can be 100% sure this is what the user wants to do. In C++, there is like billion different ways to express A equals B, right? And these complex frameworks, it's sometimes amazing that the compiler can actually figure out how to optimize that code. But nevertheless, there is so much manpower behind the C++ compilers, LLVM, right? GCC, they are making lots of good progress. So I think that's today where the focus really is. So
I see. Have you also worked on other codes in the past? Have you maybe explored SPH or LBM, these codes? And
LBM I never did. I did quite a bit of work on DM, so discrete element method, basically
yeah,
little particles that hit each other, right? Then
hmm,
the constitutive laws are so complex that they are not easily expressible in some nice closed form equation. And we are looking at SPH, so STAR-CCM Plus. It's presented a lot as a finite volume framework, and that's where the roots of that code are.
yeah,
But it's way more than that. We actually started with finite volume, and then we realized that not everything can be nicely expressed as finite volume. Sometimes, for like structural mechanics, the finite element formulation is beneficial. Same thing is at some point you want to start doing things like droplets hitting a windshield. For that, you cannot work with finite volume. What you want is proper Lagrangian formulation. So all this stuff is now part of the code. And once you have Lagrangian, meaning droplets, SPH is just one step ahead. So we actually have now SPH code
yeah.
uh, at the moment running on the CPU, but performing reasonably well. And the GPU port is in the works. So
Really interesting. And again, I'll put all relevant links to what Peter mentioned down in the description. Maybe Peter can send me also additional resources so we can add them to the description as well.
yep.
Any closing remarks from your side? Anything we might have missed, Peter? Maybe some closing remarks or motivating words to the fluid dynamics enthusiasts out there?
No, so the closing remarks, it's really nice to be able to work on something like this because you have these wow moments, right? So when you start looking at the GPU for the first time, it's like, well, there's this strange thing, and so the first wow comes when the code actually compiles for the first time. Then comes the second wow when it's starting to do the right thing, right? So it compiles, it builds, and then it also computes the results that you would expect. That's kind of
Hmm.
because technically you are running a totally different hardware than you were running yesterday. And then the third wow typically comes when you get rid of this last CPU loop. Because until you do that, there is always some sync point somewhere in your code where the kernels have to all wait until your memory is copied back to the CPU. And you don't really see this huge performance bump. But when you get that last loop out and suddenly the code becomes 40 times faster, that's really, really nice. That's very rewarding, I must say.
Yeah, that's really nice to hear. Really cool. All right. With that, I think we can wrap it up. I think 40 minutes is enough. And then potentially, if Peter wants, maybe there's some updates or maybe SPH or some other revolutionized approaches that we can talk about in the future. But yeah, appreciate it, Peter, for being on the show. I hope the audience learns a lot and speak soon.
Okay, thanks. Talk to
Thank
you
you so
later.
much.